Hi everyone, and welcome to Understand the Math. In this video, we're learning about a fundamental technique in data science, Principal Component Analysis, or PCA. We'll look at PCA from a linear algebra point of view because that's where the real intuition comes from. Have you ever worked with a massive data set where all your variables seem to be telling the same story? That's where PCA comes in. When we collect data, we often measure several variables at once, and those variables are often correlated. This means that they carry overlapping, redundant information. Take, for example, temperature and humidity readings. These variables are often related. Changes in one variable are often accompanied by predictable changes in the other. When variables carry overlapping information, we often end up using more variables than necessary to describe the data, especially in large data sets. Principal Component Analysis, or PCA, solves this by summarizing the information and creating new variables that capture the important patterns in the data while reducing the overlap. PCA is still helpful even when we don't reduce the number of variables, such as in the example with temperature and humidity, because it gives us a clear view of how the variables vary together. PCA essentially reorganizes the data into new, uncorrelated directions that reveal the main patterns in the data much more clearly. We're now going to walk through the full PCA procedure using our temperature and humidity example. By the end, you'll not only know how PCA works, you'll understand why each step matters. Let's get started. I've organized the PCA process into 5 clear steps that we can follow. The first step is to place the data into a matrix. Our data matrix is written as capital X, and each row in the matrix contains a feature or variable, such as temperature or humidity, and then each column contains a sample, observation, data point, measurement, or instance, depending on which field you're working in. The column vectors in matrix X are called observation vectors. So you can get a sense of how this works. Let's look at our example and put this data into a data matrix. We have 2 variables, temperature and humidity, so that means our data matrix is going to have 2 rows. We have 4 observations, so that means our data matrix is going to have 4 columns. Our data matrix is going to be capital X, and the first row in this matrix is going to contain the first feature or variable, which is temperature. So our entries are 80.5, 78.5, 81.5, and then 79.5. Our second row contains the humidity readings, so those entries are 58.5, 60.5, 59.5, and then 61.5. The first observation vector is x1, and it's just the entries in the first column of our matrix X, and it's equal to 80.5 and 58.5. I'm not going to write down the other 3. They look very similar. These observation vectors are important, and we're going to need them for our next step. The second step is to center the data. The goal is to shift the data so that its mean is centered at the origin. Typically, the mean of the original data is not centered at the origin. In the graph down here on the left, I have plotted the temperature and humidity readings for each of the 4 observations in our example. You can see that they are clustered up here in the right-hand corner. When we center the data, we subtract off the mean, and the data becomes centered at the origin, shown in this graph, and has a new mean of 0. So that's where we're headed. Now we just have to figure out how to get there. There are 2 steps that we need to follow to center the data. The first step is to compute each feature or variable's mean. Over here on the right, I've written down the general formula for the mean. You just add up all the observation vectors and divide by the number of vectors. Let's now compute the mean for the temperature humidity example. Here's our data matrix. And let's write down below this each observation vector. There's x1, x2, x3, and x4. Our mean is equal to 1 divided by 4 because we have 4 vectors. And then we're just going to add up x1 plus x2 plus x3 plus x4. This gives us 1/4. And if we add up all the entries in our first row, we get 320. And then all the entries in the second row add up to be 240. So our mean is equal to 80 and 60. So that just means the mean temperature is 80 degrees and the mean humidity is 60%. The second step is to find the centered observation vectors in centered data matrix. The formula for the centered observation vectors I've written as x sub j hat, and it's just x sub j, which is our observation vector, minus the mean. The centered data matrix is x sub 0, and it just contains the centered observation vectors. I'm going to show you how to compute one of the centered observation vectors. Let's compute x1. So we have x hat 1. That is going to be equal to x1 minus our mean. Looking up above, let me highlight it so you can see what I'm looking at. This is x1. So we have 80.5 and 58.5. And then we subtract off the mean, which we found to be 80 and 60. And this gives us a value of 0.5 and minus 1.5. You do the same thing when computing the other centered observation vectors, and we put it all together, and we can now write down our centered data matrix. It's 0.5 minus 1.5, and then we have minus 1.5 and 0.5, and then 1.5 minus 0.5, and then finally minus 0.5 and 1.5. There's one other thing I want you to notice before we go on. If we were to compute the mean of this centered observation data, you can see if we add up all the entries in the first row, we get 0, and all the entries in the second row, we also get 0. So our mean, we'll call this m sub 0, is equal to 0. This just means that the mean is at the origin. These centered observation vectors are the points that we plotted up here on the right-hand side. And you can see that they are centered about the origin because the mean is equal to 0. Now we can move on to step 3. Step 3 is to find the covariance matrix. The covariance matrix is a square matrix, and it contains the variances of each variable along the diagonal and the covariances between the variables in the off-diagonal positions. Each variance along the diagonal of the covariance matrix tells us how much each variable spreads out, and then each covariance in the off-diagonal positions shows us how two variables change together, either positively or negatively. Over here on the right, I have written down the formula for our covariance matrix. We're going to call it matrix S, and it's just 1 over n minus 1 times the centered data matrix times the transpose of the centered data matrix. Let's now compute the covariance matrix for our temperature humidity example. Let's go ahead and let's rewrite what our centered data matrix is. And let's also write down what n is equal to. We have 4 column vectors in our matrix, so n is equal to 4. Now we can compute S. Matrix S is equal to 1 over n minus 1, so this is 1/3. And then we have our x0. And we're going to multiply this by the transpose of our data matrix. This just means the first row becomes our first column. And then our second row becomes our second column. When we multiply all of this out, we end up with an answer that looks like this. We have 5/3 along the diagonal entries, and our off-diagonal entries are -1. The 5/3 values are the variances, and then the -1 values on the off-diagonal are the covariances. I'm going to write down a general formula for S just so that you can see. The first entry is S sub t squared, and then we have the covariance of t and h, and then in the lower right, we have the covariance of h and t, and then in our other entry along the diagonal, we have S sub h squared. This matrix will always be symmetric, because it's a matrix times the transpose of the matrix. In our example, S sub t squared is equal to S sub h squared, and it's equal to 5/3. Because these numbers are the same, this tells us that t and h vary by the same amount. If we take the square root, we can see that S sub t is equal to S sub h, and it is the square root of 5/3, which is approximately 1.29. This tells us that t and h values lie about 1.29 units away from the mean. Which is at the origin. Now let's look at the covariances. The covariance between h and t is equal to the covariance between t and h, and it's equal to -1. This tells us that t and h move in opposite directions. In other words, when one goes up, the other is going to go down, and vice versa. Now that we have the covariance matrix, we can go on to step 4, where we're going to find the eigenvalues and eigenvectors of the covariance matrix. Since the covariance matrix S indicates how the data varies, its eigenvalues and eigenvectors are going to indicate the amounts and principal directions of that variation. Eigenvector V1 will be the direction with the largest variance, and its associated eigenvalue lambda1 will be the variance along that direction. Eigenvector V2 will be then the direction with the next largest variance, and this pattern continues for the other eigenvalues and eigenvectors. Since the covariance matrix is symmetric, let's go back and look at that matrix. It's right here, or more general here. A symmetric matrix is just when the entries across the diagonal are the same. Because it's symmetric, all the eigenvectors are going to be perpendicular, And then, because the covariance matrix is positive semi-definite, all the eigenvalues are going to be non-negative. And this makes sense because they measure variance, and variance can't be negative. We're going to first find the eigenvalues of the covariance matrix because you always have to have the eigenvalue before you can find the eigenvector. Over here on the right, I've written down the formula that we need to follow to find the eigenvalues. Our covariance matrix S is equal to 5/3, -1, -1, 5/3. Our formula to find the eigenvalues is the determinant of S minus lambda I is equal to 0. This means that we are just going to subtract lambda off our main diagonal entries. And we set that equal to 0. This gives us 5/3 minus lambda quantity squared minus 1 is equal to 0. So we have 5/3 minus lambda squared is equal to 1. That gives us 5/3 minus lambda is plus or minus 1. And that tells us that lambda is equal to 5/3 plus or minus 1. And that is going to be 8/3 and 2/3. You always want to set your first eigenvalue equal to the largest eigenvalue. So we're going to let lambda 1 be equal to 8/3, and we're going to let lambda 2 be equal to 2/3. We're going to need those in a minute, so let's go ahead and let's highlight these. Before we go on to talk about the eigenvectors, let's talk about what these eigenvalues tell us. The total variance is equal to lambda 1 plus lambda 2, and this is equal to 10/3. To find the total variance, you just add up all the eigenvalues. We're going to use this to find out how much variation or structure in the data can be explained by each principal component. Principal component 1 is going to explain lambda 1 divided by lambda 1 plus lambda 2. That's just the total. So this is 8/3 divided by 10/3, which is 8/10, and that is 80%. This tells us that principal component 1 explains 80% of the variation, and this tells us that there is a strong dominant pattern in the data. Let's look at PC2. This is lambda 2 divided by lambda 1 plus lambda 2. Since we only have 2 of them, we know it's going to be 20%, but let's just walk through the calculation. So this is 2/3 divided by 10/3, 2/10, and we get 20%. So principal component 2 is only going to explain 20% of the variation. Now that we know the eigenvalues, we can find the normalized eigenvectors of the covariance matrix. Over here on the right, I have written down how we go about finding these eigenvectors. Our covariance matrix S, once again, is 5/3 minus 1, minus 1, 5/3. And then let's write down lambda 1 and lambda 2. Lambda 1 is 8/3, and lambda 2 is 2/3. Let's first find eigenvector V1, and this is going to correspond to lambda 1 is equal to 8/3. We're going to take S and subtract lambda I, and we're going to augment that with 0. Let's see what this gives us. We have 5/3 minus 8/3, and then minus 1, and then we have minus 1, and then we again have 5/3 minus 8/3, and we're going to augment that with 0. This is then equal to, oh, this is nice, minus 1, minus 1, minus 1, minus 1, augmenting it with 0. Now we go ahead and reduce this to reduced echelon form. We could almost just do this in one step, but I'll go ahead and take 2 steps. Our rows are duplicates, so our second row is going to just become 0. And then we can multiply our top row by -1. I'm going to let U be our unnormalized eigenvector, and we can use this to find our normalized eigenvector. So it's U1, U2. If we go over here to our top row, this tells us that U1 plus U2 is 0. So U1 is minus U2, and we can add this in. U1 is minus U2. Pull the U2 out, so we have U2 times minus 1, 1. Now we get to choose U2. It's really nice if our first component in our vector, I'm looking at this component right here, is positive. So I'm going to choose U2 to be -1. And this tells us that U is equal to 1 minus 1. Now we need to find its magnitude. The magnitude of U is just the square root of 2. So we can write down that our normalized eigenvector V1 is equal to 1 divided by root 2 minus 1 divided by root 2. Eigenvector V1 is the direction of the PC1 axis. And this new axis is the line y is equal to minus x, because our components have the same value and they're opposite in sign. Let's now find our second eigenvector, V2. And let's just remind ourselves that lambda 2 is equal to 2/3. We are going to go through the same type of analysis that we did for our first eigenvector. We have s minus lambda I, and we augment that with 0. Let's see what this gives us. Our s was 5/3, so we have 5/3 minus 2/3. We have -1s on the off diagonal, and then another 5/3 minus 2/3. And this gets augmented with 0. This is equal to 1 minus 1 minus 1, 1. We'll put this in reduced echelon form. The rows are the same, just negatives of each other. So the second row goes away, and we have 1 minus 1, 0, 0. And that's augmented with 0. We again take our vector U, let it be equal to U1, U2. Our top row tells us that U1 minus U2 is 0. So we have U1 equal to U2. That means down here, we can just pull out a U2, and we have 1, 1. Let's set the U2 equal to 1, and we have an eigenvector 1, 1. This eigenvector also has a magnitude of root 2, and that tells us that our second eigenvector is equal to 1 over root 2 and 1 over root 2. I forgot up here to highlight our first eigenvector, and then we'll highlight our second one. Let's think about what the second eigenvector tells us. Eigenvector V2 is in the direction of the PC2 axis. And because those components are the same, this axis is the line y is equal to x. In the graph down here on the left, the PC1 axis is in blue and the PC2 one is in orange. PCA finds a new set of perpendicular axes called the PCA coordinate system by just rotating the original coordinate system so that its first axis points in the direction of the greatest spread in the data. We'll see what this rotation looks like in our next step. In the next step, we are going to be computing the principal component scores, and to do that, we'll need a matrix that contains the eigenvectors. So I am going to create a matrix V, and I'm going to let it be equal to our eigenvectors V1, V2. And we'll need that here in a second. We can now complete the last step, finding the principal component scores. The principal component scores are the new values each data point has when written in the directions of the principal components. The principal component scores are contained in matrix Y, and that matrix is equal to the transpose of our eigenvector matrix times our centered data matrix. Let's first write down what matrix V is. We just assigned matrix V to be V1, V2. Now we can go ahead and put in those vectors. V1 was 1 over root 2 minus 1 over root 2, and then V2 was 1 over root 2, 1 over root 2. To make our calculation easier, I am going to pull out the 1 over root 2, and then our matrix is just 1 minus 1, 1, and 1. Now let's go ahead and compute Y. We have V transpose. Let's bring out the 1 over root 2 first, and now we'll take the transpose of matrix V. Our first row becomes our first column, and then our second row is our second column. And then we're going to multiply this by our centered data matrix. And that matrix looks like this. Now we just have to multiply these two matrices. I won't do that here in this video, but here is what we end up with. To make the principal component scores easier to plot, I'm going to round them to 2 decimal places. This gives us 1.41, minus 1.41, 1.41, and then minus 1.41. I know this example is pretty simplistic, but I think by looking at a simple example, it really helps you understand PCA. The first row of matrix Y contains the PC1 scores, and then the second row contains the PC2 scores. These values tell us where each observation lies in the new PCA coordinate system. Down here at the bottom, I have plotted our new axes and points. Just so that you can understand this better, this is point 1, this is point 2, and then we have point 3 and point 4. Notice in the graph that the points spread out more along the horizontal PC1 axis. The reason for this is that PC1 accounts for 80% of the variation. So the higher the variation, the more the points are spread out. Notice then that the points are spread out less in the vertical direction. And this makes sense because PC2 only accounts for 20% of the variation. Now let's understand better what these values translate to in our example with temperature and humidity. Remember that V1 was equal to 1 over root 2 minus 1 over root 2. The components in the vector are the same value, but one is positive and one is negative. This tells us when PC1 is greater than 0, we are going to have a higher temperature and lower humidity, because when one goes up, the other goes down. When PC1 is less than 0, just the opposite happens. The scores correspond to lower temperature and higher humidity. Let's now look at our second eigenvector. Its components were equal. The second principal component scores point in a direction where temperature and humidity rise or fall together. Positive PC2 scores correspond to when temperature and humidity are above the mean. And then negative PC2 scores are when temperature and humidity fall below the mean. You can see that these conclusions are true when you look back at the original data for humidity and temperature and look at points 1, 2, 3, and 4. So that's the complete PCA procedure. Principal component analysis removes the correlation in the variables and rotates the data so we can clearly see the main pattern of variation.